contravariant function from associative algebras to associative algebras. And an interesting example that appears in topology is comes from chains and cochains. In fact, if you consider some a simply connected complex K, you can consider the cochains with the cut product, and this is associative algebra. And the dual, its dual, will be weakly equivalent to the chains on the loop space of K. So the loop space has a Pontryagin product just by concatenation of loops, and this induces on chains an algebra structure. Okay, so this is an example of an incarnation of this duality for algebras. Now I want to go to the meta level of differential graded operads. So we are, I don't know if you are all familiar with operads, but I hope that you are.
I guess you can assume that, yeah.
Okay, thank you. So the generalization to the world of operads of the bar construction. So what we can do is that we take basically the free cooperad on the collection coming. So you basically take I'm looking at operads in chain complexes. So I can take just the suspension, the degree suspension of my operad, arity by arity, and then I consider the free cooperad over it. So you know that basically this is given by trees. An object of this free object of the free cooperad consists of okay, it's described by some tree with vertices labeled by elements of the operad. So I'm not gonna write a formal definition, but you have some. Okay, and then there are some leaves that are numbered. So I don't want to give the precise definition, but this is a little is the idea that is behind this construction. And then the differential splits into two parts here. So one is the differential that comes from the differential of O, the internal differential, and the other one is the external differential. The external differential is given by the composition in the operad. So the composition in the operad can be visualized as a map. These are the so-called circle K composition, going from say the arity I elements or O of I times the arity J element O of J into elements in arity I plus J minus 1. And so what and this gives a differential basically induced by collapsing edges in these trees. So when I collapse the edge, I replace, if I have some vertex here in the set by X and some vertex Z, some vertex in the set by Z, I just collapse this and I get a single vertex of another tree with which is labeled by the composition of Z and X and the operad composition of Z and X. Okay, so this was defined by, I would say, Ginzburg and Kapranov originally, the bar construction for operads in chain complexes. And the cooperad structure is given by degrafting, so by splitting a tree into two parts. So you can split, basically cut an edge and decompose a tree into two trees. And this is the coproduct in this cooperad. Now, you can take the linear dual, and this is an operad. So again, we get a contravariant factor. This time it goes from operads to operads in chain complexes, and this is also an involution. So if you apply it twice, you get back up to homotopy or up to weak equivalence to the original operad in chain complexes complexes that you have under mild assumptions, so finite type and concentrated in, say, positive degree. Okay, so just some examples, some classical examples now. If you apply this functor D to the associative operad, then you get back the same associative operad up to a shift. So what is this shift? This shift means, okay, when I shift, in fact, it's not the same shift that appeared before, because before I was just changing the grading by adding one. But here the shift in the sense of operad, in RTK, I have to suspend by k minus 1 times the chain complex in RTK. And then actually I have also to take a tensor product by a sign representation, to be precise. So, but anyway, what is important about this is that if you take the suspension of an operad, you might ask yourself, what are the algebra over this operad? They are exactly the algebras over the original operad by up to a shift. So it turns out that SO algebras is the same as O algebras shifted by -1, by degree -1. So up to a grading, basically, I get again the same kind of algebras. And this is for the associative operad, is self-dual. And if you look at the commutative operad, then the dual of the commutative operad is the Lie operad, up to a shift by 1. So there is this duality between this now classical duality, I would say, between com and Lie and us and self. Okay, and this duality functor is important because also induces a functor between the algebras over the operad you started from and the operad you get after applying the bar duality. So basically, you can go from O algebras to DO algebras, and in particular, if you consider O equal to associative operad, then we get the duality for associative algebras we were talking at the beginning of the talk in the first slide. So you have a contravariant functor from associative algebras to associative algebras. And if you apply this contravariant functor to the case of duality between commutative and Lie algebras, you get contravariant functor with from commutative algebras to Lie algebras, and vice versa, a contravariant functor from Lie algebras to commutative algebras. And at the level of monotopic categories, this gives rationally, this gives an equivalence. If you restrict to, again, finite type and the correct connectivity. And this is the duality that appears in the classical rational homotopy theory between the theory by Quillen in using Lie models and the theory by Sullivan using commutative models. So this is a well-established duality, right? Okay. So the next question is, okay, how about the little cubes operad or EN operads? So EN operads are operads that are weakly equivalent to little n cubes operad. So these are topological operads, but we can take the chains on them and we get operad in chain complexes. And also actually we could take the homology, it's even easier. So we could take the homology with coefficients, say, in Q or characteristic 0. And this is what people call lowercase en. So how about lowercase en? If we apply the duality functor, so the bar duality, what do we get? And it turns out that up to suspension by n, but it is exactly En itself. And this was proved by Gessler and Jones. So this is the first, the first duality that we knew for En operads. It's more subtle if you, instead of going to homology directly, you go first to chains. You can consider the chains, and basically the same duality holds. So if you consider chains on En, and then you apply the duality factor, the bar duality, you get the same up to weak equivalence and up to a shift by N. This is more subtle and was proved by Benoit Fraisse, this self-duality.
Excuse me, Paolo.
Yes.
Is this would this follow from the formality of the En opera, of the like chain level En opera?
Yes. In characteristic 0 it does, but this is true with the integral coefficients. So this is over Z actually.
Got it. Thank you.
You're welcome. Okay, so yeah. So now you can ask yourself, okay, since we have this self-duality for the chain operator over En, we also have a functor that goes from algebras over chains on En to itself. So these are also called N algebras. And algebra is the same as this is the same as C star En algebras. And this functor has also an interesting geometric meaning. In fact, it generalizes the Adams duality that we had before for N equal 1. So this functor relates exactly. So if you have an N-connected complex, K, you can consider the cochains over K, and this is an infinity algebra. Cochains over any space form an infinity algebra, but you can just forget and remember that it is an En algebra, and then you can ask yourself what is its dual N algebra. The dual N algebra will be the algebra of chains over the n-fold loop space of K. In fact, the n-fold loop space is naturally an En algebra. And so you can apply the chain functor, and the chains over the n-fold loop space will be an N algebra. Okay, it is N algebra. So if the connectivity of the complex is at least N, then these two N algebras are related by the duality. This is another theorem by Benoit Fraisse.
Oh,
okay, so the next.
What if
yes.
On the previous slide, what is the En structure in the En algebra structure on C upper dot K on the cochains?
Okay, on the cochains, it is the so there is a McClure-Smith description. So McClure-Smith describe for at least for simplicial cochains. So at least for say simplicial complex, there is an infinity algebra structure on the normalized cochains on K. And so I'm looking at basically, if you like, yes, some. I look, or you take the singular cochains on space, and then yes.
So it's infinity reduced to En.
Yes, exactly. Right. Now the question is, can we do something like this topologically instead of just on chain complexes? So in order to make sense of this, we first have to define what the bar construction for topological operads is. And this was done separately, independently in my thesis and Michael's thesis. And then we basically met afterwards and we started working together. So in fact, Michael defined this simplicity and I define it cubically. So if you start from topological operad O, and I want it to be reduced to make life easier, so this means that O of 1 is just a point, then I can consider the following space. So if you know what the W construction is, it helps, but the W construction is a so-called Borman-Vogt resolution of topological operads. And you can visualize it as being described by trees, where you have the vertices are labeled by elements of the operad, like this. This is in O2, this is in O3, for example. And then, okay, and there is some labeling. And then there is some length on the edges that can vary between 0 and 1. And then there are some identifications. So when the length is 0, you can compose your labels. And when you compose, so this is an operad. When you compose two label trees, you insert a new edge that has length 1. So this is said in 2 words, is the resolution by Borman-Vogt. So this tree is label 3 is an element in WO4. Okay, now the boundary of Vogt construction is the subspace of decomposable elements. So this is the same as elements that have some length with with some edge of length 1. So what I do is I collapse by the subspace of decomposables, and then I take the suspension. And this is exactly the RTK space in the bar construction of O. And this turns out to be a base space. There is a pointed cooperad structure. So you basically, the monoidal product is the smash product of pointed topological spaces. And the coproduct is given again by decomposing trees into 2 parts. So by cutting trees along some internal edge in 2 parts. And this is the right notion because, okay, maybe I, okay, maybe, okay, sorry. Okay, this is the right notion because if, for example, your operad is a CW operad, so the spaces are CW complexes and the composition maps are cellular, then the cellular chains on your operad form an operad in chain complexes, and the algebraic bar construction of the cellular chain complex is exactly isomorphic to the cellular complex of the bar construction. So this is really the upgrading to the topological world of the bar construction.
Paolo,
okay.
Paolo,
yes.
I have one more question, sorry. How do you know where to cut the edge when you do the co-product, the co-operad structure? Because the edge has length, and you want to cut it somewhere.
Yes, good point. So basically, if I have some circular composition, then so the circular composition like singles out some indices, like maybe you have indices from I to I plus j minus 1, and then you continue till, okay? So suppose that I'm doing some circular composition correspond that Yes. So I'm doing something like sorry, yes. OH, okay. And then circle I. Sorry. Okay, the idea is that if the when you do the circle I composition, if the relevant indices like this belong to a subtree, like this, so it goes from I to I plus j minus 1, and all the others are away, then you can cut. Otherwise, you just get a base point. So the trick is that you cut when you cut and you get the right indices in the right position. Otherwise, you don't. You just get a base point.
Yeah, but my question was, when you cut, oh yeah, I see. So the external edges don't have a length. So when you cut an edge at some point, an edge of length t, you basically forget the length of this edge. Is this right?
Yes.
Yeah.
Not exactly. Okay. Yes, this is another good point. Because if you notice, there is a suspension here. So the suspension is basically means that I have an extra parameter. I consider it as length of the root.
Oh, I see.
So basically, when I cut, I remember this. If there was some parameter here, I remember it as parameter of the root of the upper tree. So there is an extra. This bar construction with respect to the W construction as an extra parameter. And this is okay. This is the trick.
Okay. Thank you.
Okay. So just an example, if you do it this bar construction for the associative operad, then you get W construction of associative operad gives you the associahedra, and then there is a symmetric group because we have many components. But then you have to quotient out the associahedron by its boundary and then take the suspension. So this is what we get. And okay. Just to give an example. So I have to go from suspension of associahedron where I collapse the boundary. So if I want to describe the coproduct in this cooperad, it is easier to say that is applied by applying one point compactification factor to an open embedding. So what happens is that we have we embed some square into the pentagon, and then we this is an open embedding, and then you you apply one point compactification. So basically, you collapse everything outside the square to a base point. And that there is also an extra parameter, this is a suspension parameter. Yeah, so let's see. Okay. Yes, okay. So it will be probably even clearer later. So now I want an operad back. So I was going from topological operads to pointed topological cooperads, and I want to dualize them, but I cannot do it in topological spaces. I can do it only in spectra. So if I have my topological operad O, I can take its suspension spectrum, and this is an operad spectra. And then I can take, in fact, maps. This is really base map, so there is no base point. So maps of the pointed cooperad BO into the sphere spectrum. Okay, and this turns out to be an operad in spectra. So this is the version in spectra of what we did before in chain complexes. I start from in fact, topological operad, and I get a spectrum operad. Now I want to see that the EN operad is self-dual in spectra with respect to this construction. So if I start from EN, I apply this D, I get again the same EN operad in spectra up to a shift. However, there are many things that need to be explained here. Okay, so there was a lot of evidence for this fact that the self-duality holds in spectra, because you remember the duality between operads induced some functor between the corresponding algebras, and we have a functor between EN algebras and EN coalgebras that was constructed by Ayala and Francis. So they expect somehow that there should be behind this self-duality of operads, EN operads in spectra. And a similar construction was given by Lurie. But nobody constructed explicitly this duality in, in spectra. So, okay, how about suspending and desuspending topological operads or spectral operads? This is the first problem. We have to make sense of this. So the first approach to suspending and desuspending operads in topological spaces was given by Aron, Greg Aron, and Maria Cancarinta. So they construct an operad S of spheres. So the elements are spheres, these are topological operads. And they are given just by collapsing the boundary of a simplex in, okay, the simplex K minus 1. If you consider the fact that, so you describe the point in the simplex by simplicial coordinates, you can, so the simplicial coordinates, they are positive, they add up to 1. You can multiply the simplicial coordinates, and this gives you an operad structure on these spaces. And they're very nice because they are not only homotopy equivalencies, the operad composition maps, but they are homeomorphism. They are exactly homeomorphism. So if you like, this is both operad and cooperad, because you can both compose or decompose uniquely somehow elements. And since we have this operad, this is very useful to define the suspension of operads so in topological spaces and even in spectra. So you can define the suspension by smashing your arity-wise your operad with this sphere operad. And you can also desuspend by taking instead the mapping spectrum. So in arity K from SK to OK. Okay. So this is a handy way to define the suspension topologically. However, there are some missing features. For example, if you think about our operad of little cubes or little disks, this is an operad in ON spaces. So if you think about it, so little disks is operad in, so little n disks is operad in ON spaces. This is always the real orthogonal group, is not the operad. Sorry for the notation. And somehow this suspension is not compatible with the orthogonal group action. If you think about the duality said that you suspend n time, desuspend n times. So basically, if you apply the duality functor, this amounts to the suspending n times, but I want to make sense of some orthogonal group action here. So I want to find some more refined structure for the suspension. Okay. Now, this is one thing. And yeah, so maybe I should, okay. Maybe I can tell you already, spoiler, but I can already tell you something. So you want orthogonal group action. So I can define what we call the barycentric opera. This is a kind of generalization of this simplex opera, but is also compatible with orthogonal group action. So what is that? This is very general because this works in any normed space. So I consider a finite dimensional normed space, and this is useful because it can describe at the same time both the little cubes and the little disks. In fact, if you think about the little disks, how they are defined, and the little cubes, you're just asking that basically the norm of the difference between the centers of the disk is not less than the sum of the disks. And similarly, the fact that they are inside the unit disk or the unit cube. So they can both define just using a norm. Okay, so if I have a normed space, I can define this barycentric opera. So barycentric opera is basically, I consider points with in my space with some weights. These Ti are some weights that are, in fact, element of the open simplex because the sum of the weights is 1 and they are positive. And I'm requiring that the barycenter of the points with respect to these weights is the origin. So this defines a certain vector space. And the nice thing is that there is an operad structure on this collection of spaces, RV, such that there is an operad composition that again has homomorphism as structure maps. Okay? And the structure maps here are, if you think about the little disk composition, if you try to write down the little disk composition operad in formula, it's exactly the same formula. The only difference is that here there is no restriction on the disk, so they might overlap if you wish. Okay. So you have some points that you think of as centers of some disks, and then you have some radii, some numbers, positive numbers that you think of as radii of the disks. And if you think about the composition in the little disk operad, there are some formula that gives you really a linear map, okay, a linear formula. And this is the operad, the barycentric operad formula. The advantage is that the orthogonal group, so the isometry group with respect to the norm acts on these spaces, and the composition map is equivariant. Okay, so I have to speed up, I think. So, okay. So in order to prove the theorem, we have to use at least 2 different models for the n operads. One is the Fulton-McPherson operad Fn, this kind of extension to a higher dimension of the associaedra. And you might know that this is a compactification of configuration space in Euclidean space Rn, modulo translations and positive dilation. Okay. So in fact, there is a related thing that, okay. So I haven't written it down, but I proved in my thesis that if you apply the W construction by Borman and Vogt to Fulton-McPherson, you get again Fulton-McPherson, but up to isomorphism. So it's not homotopy equivalence, but it's really isomorphic to it. And this is very useful because if you basically, okay, it turns out that if you apply the bar construction instead to Fulton-McPherson, this is a cooperad. Remember, it's a pointed cooperad. Is isomorphic to a certain pointed cooperad. It is obtained by applying the one-point compactification factor to a certain operad UN of open embeddings. So there is a nice structure of on this base of operad on this basis. So consider the just configurations, equivalent configuration in Rn, and then you mod out by translation, but only translation, not dilation. And you don't compactify, you don't do anything, just that open set. And this collection of this UN forms an operad. The only thing is that there is no nice formula. So this comes just from this isomorphism. So it exists, but there is no explicit formula that you can write down. And if you apply the one-point quantification factor, you get exactly BFN. So this shows that somehow that the duality is true, at least arity-wise. Why is that? Okay, because our UN is an open set in Euclidean space, and so it is a spinor-weighted dual to its one-point quantification. Now, okay. Now, what is the duality? The duality factor applied to Fulton-McPherson. This is the same as taking the spinor-weighted dual of BFN, but BFN is UN one-point compactified. But as we saw here above, the spinor-weighted dual of one-point quantification is the space UN itself, okay, up to a shift. So basically this is telling us that arity-wise, it is true that the dual operad has the right homotopy type. But the most difficult part was in our project was to show that there is a coherence at the level of operads. And this was quite complicated. So it took us many years. And we also had in mind that we had this barycentric opera. This is the right dualization object somehow. But we were missing the exactly the strict operad map that realizes this duality. So this is what we had to do. Okay, so this is what I was telling you before, that this is the barycentric operad. Okay, in arity I. Okay, here I'm looking more generally, instead of talking about arity K, I'm looking at finite sets. So I is a finite set. All right. So now we might want to intersect the barycentric operad and the usual little disks. So the usual little disks are given by this condition, of course, that I mentioned before. So you want the distance between the centers of the disk are not less than the sum of the radii, and also the norm of the center of the disk is not more than 1 minus Ti. Okay. So we have these conditions, but in addition, we also have this barycentric condition. So the weights, so basically the barycenter of the centers of the disk with respect to the radii is the origin. And it turns out that this obviously is a suboperad of both. So this is an operad that we call the restricted little disks. And it is a suboperad of the little disk. But it is not trivial to show that it is not equivalent to the little disk. It is weakly equivalent. So we really had to work hard to show that this subspace, this small operad, is an EN operad. And in order to do that, we had to play with some vector fields that basically some deformation retraction of the full little disks into these restricted little disks. This is related to work by Baryshnikov and Kale and Bubenik. They look at hard spaces of hard disks where you fix the radius of the disk, and under some condition, these spaces are homotopy equivalent to the usual configuration spaces. But this is kind of the limit case, because the sum of we want like varying the radii vary, and the sum of the radii is exactly 1. So it's kind of the critical stage. If you pass this critical stage, the topology changes. This is what Baryshnikov and Kale did, and Bubenik. So we had to use this restricted little disk, and also for the Spiner-Whitehead pairing, we have to introduce some operad of spheres. And here the correct thing is to look at something like, okay, collection of disks where each disk contains the origin and contains the centers of all the other disks. So, well, okay, more or less. So each disk must contain origin and the centers of all the other disks. Under this condition, you get not a sub-operad, but a sub-operad of the barycentric opera. But if you apply 1 point compactification, then it becomes an operad. So we get an operad of spaces that are homotopy equivalent to spheres, and they are the right objects in order to get a dualization. So now we have all the ingredients, and we can define explicitly the duality map. So the duality map is like a Spanier-Whitehead pairing. So this is a sphere. This is the space coming from the EN operad. This means Fulton-McPherson space in the vector space V. And this is bar construction applied to the little disks. Bar construction on, in fact, on the restricted little disks. Yeah, so basically I have these two spaces, and I construct an S-duality pairing between them. And the map is explicit, in fact. There is this explicit formula where you use all the ingredients that you need. So you use, so this Y is an element in Fulton-McPherson space, so it is a configuration. And so basically you're using, you normalize parts of this configuration, and they come into this formula, this Y of E, I. And then there are the length of the edges in the bar construction that are this RE. And then there are the elements in the restricted little disk. So both the centers of the disk and the radii of the disk. And this gives an explicit element here. And the good thing is that this is really an operad map, because this is linear somehow, and also the barycentric and the little disk, restricted disk maps are linear. So this is exactly in a map of operads. After you take the adjoint. So the adjoint goes from Fulton-McPherson to maps from the bar construction into the sphere operad. These are strict maps of operads in spectra. And okay, the idea of the proof is basically comes from what I said before, that we know the right, that the topology, the homotopy type is the right one. And in addition, we use the fact that this is the Told-Puppe description of Spiner-Whitehead duality, where basically you have a complex. So this is kind of general thing. Okay, it's not when you have a finite complex, then you have a star-shaped neighborhood of the origin. Then let's see if it's correct? Yes. And this is a neighborhood of your finite complex. Then this addition in Rn is adjoined to the Spanier-Whited pairing. So this is the, and somehow the fact that our maps are linear is exactly gives this duality pairing. This is the trick. Okay. So let me mention last thing that you might ask yourself, okay, how about if I have the inclusion of En into En plus 1, then what is the duality map? It goes from, so it's contravariant. So after I apply the duality map, I should go from Sn S minus n plus 1 of En plus 1 to S minus n of En. And these maps, in fact, can be realized. Originally, they were defined by May, and then Kuhn and Ahern topologically. And in fact, they can be described as strict operad maps in our context, and also compatible with the orthogonal group action. So somehow we we are able to define the duals of the inclusions. And in particular, if you apply to the standard inclusions like this, you get an inverse tower. And this inverse tower defines, okay, it's a way to define the Lie operad in spectra without using a Koszul dual bar construction. You just take the inverse limit of this tower. Okay, thank you. I think this is all what I wanted to say.
Okay, yeah. Let's thank Paolo for the very interesting talk. Oh, any questions? Oh, what happened? Oh yeah, he stopped sharing. I
found something on top.
Like the last time around. Yeah. So okay. Any questions?
Yeah. So these shifted operads, so in the McClure-Smith paper, they construct these like simplicial looking things where, but the degrees in their operads are shifted down in chain degree from the number of terms in the simplicial complex. Are your shifts related to those, or?
Sorry, I didn't understand.
Here, let me try and get closer.
Yeah.
So in the McClure-Smith paper on cochain operations, they construct these kind of strange operads that look like they come from simplicial sets, but the degree is shifted from the kind of simplicial degree. Are those related to your shifted operads that you're talking about here?
Okay. Okay, you're talking about operation on simplicial on cochain complexes, or?
Yes, they have these like sequence operad type things.
Surjection.
Yeah, or the surjection operad. Yeah.
Yeah.
Right.
I
see.
But the boundary formula in the surjection operad looks simplicial, but it's in the wrong degree. You know, the degree of an element is like k plus the degree it would be simplicial.
Right. Okay, I see what you mean. Okay, I see that. Okay, the surjection is some kind of multi-simplicial, or is some kind of multi-simplicial thing, but it's not an operad in multi-simplicial complexes either. So I don't know if it is directly related to our construction, in fact.
Okay. Other questions? let me ask you a question. Is it fair to say that, you said that the biggest problem was to check compatibility with opera compositions? Like it took you most time to complete this. What is kind of a basic idea of overcoming this difficulty? Is it because you used ON invariance, or is it because you used this generalization of the little disks operad to the restricted operad related to vector spaces? What really allowed you to check compatibility with compositions?
Yeah. I think both the fact that working with these restricted little disks, they are inside this barycentric opera. So the barycentric opera is the right object to get dualization, and the fact that the formula is linear there is also crucial because it is exactly what you need for spinal white duality. So somehow both these ingredients together was led us to success. But it took us some time, because we knew the barycentric opera, but then we were trying to do more complicated things to have the dualization map. But then we realized that it is linear, so it's exactly what we needed somehow.
Is it the pure luck that things worked out this way, like linearly?
Yeah, I mean, this is the only proof I know, but
I see. Okay, very interesting. Other questions? I guess I anyway have to go. Let's thank Paolo for a very interesting talk again. I'm trying to organize, since it's basically the first days of spring, really here in Minnesota, I'm trying to organize after seminar topology beer and suggest together in the courtyard at 4:40. So everybody is welcome. Paolo, you are welcome too, but unfortunately, I'm not sure you will be able to.
Yeah, I'd like to.
Only they didn't discontinue the Concord.
Yeah. All right. Yeah. Thank you very much, Paolo. It was really nice to see you again. And
thank you, Sasha. After so many years. Oh.
Yeah. We'll see each other sometime soon. I'm pretty sure.
So,
yeah. Okay.
all the best,
All right.
Sasha.
Thank you. Yeah. Bye bye.